We've already learned how to solve systems of equations using the elimination method. We were able to do that with both two variable systems and three variable systems. But what we're now going to be able to do is use a different method, referred to as using matrices, in order to do the same task. And oftentimes, as you get used to this becomes a little easier because you can manipulate these matrices without ever having to deal with the variables themselves. So a matrix is nothing more than just a rectangular array of numbers that are broken into different rows and columns. So in our problem, the entries that we put into the matrix will be simply the coefficients of the system of equations. So I can create a matrix by just putting in brackets here, the coefficients of 2, -1, and 1, 1, 1, and -1, and -1, 2, and 2. Now, each row in this new matrix will represent a corresponding equation. Each column in this matrix will represent the coefficients for a particular variable. And so 2, 1, and -1 represent all of the coefficients of x, and so on. Now, to augment something means to enhance or to add on to. So what we're going to do is we're going to augment the answer column after this vertical dotted line, just so that we can actually show that this is separated from the rest of the system by being the actual answers to each equation. And so now this is a matrix, this is a system of equations, and we're going to be able to just manipulate this matrix to somehow find the answers for x, y, and z. Now, the system of equations can be solved very similarly to the way that we did the elimination method. So what we're going to see is that every single change that occurs in the matrix represents an identical change to the system of equations if we were to use the elimination method. So let's go over a few different things that we're going to be able to do with this matrix. First of all, if this is the system and we created the matrix, what are some things that we were able to do with the system of equations that we may also be able to do with this matrix? Well, the first thing is that we could rearrange any two equations. Meaning, if I wanted to, I could move this equation to be the first equation written and move this to be the second one. So I could just interchange these two equations and it doesn't change the system, it just changes the order. Well, since each row indicates a corresponding equation, then that must mean that I can flip interchange two rows. So I would move the 1, 1, -1, -2 up to the first row, and then maybe remove the 2, -1, 1, and 5 down to the second row. Now we always show the notation for these row operations by labeling them with subscripts. So we call this this top row R1, R sub 1. This second row would be R sub 2, and this third row would be R sub 3. So if I wrote R3 interchange with R1, that would just mean in the next operation I'm going to interchange these two rows. Well, what about another thing I can do with an equation? Well, I can multiply both sides of any equation by some non-zero number. So maybe I choose to multiply this equation down here by 2. Well, if I do that, if I multiply equation 3 down here by 2, this would become -2x, +4y, +4z, and 2. Well, that must mean that I could multiply a row by a non-zero number as well. So since rows are equations, I can also just choose to multiply one of these rows by a number. And the way that we indicate that is just by showing that I'm multiplying row 2 times 2. And the last thing we're going to do is the actual process of elimination. But we're going to be able to accomplish this in one step as opposed to 2 to 3 steps of the elimination method. For instance, if I take a look at this system of equations right here, what if I wanted to eliminate x from the first two equations? Well, I would need to see an opposite for this term right here. So since this already says 2x, I would like this second one to be negative 2x. So the first thing I would do would be multiply this entire equation by negative 2. And then in the next step, I would add these two equations together. So 2x minus 2x would cancel, and then I would combine the y's and the z's and the constants. Well, the row operation with matrices actually combines this into a single type of operation with this notation. This would mean let's multiply row 2 by 2, and once we multiply each of these elements by 2, we're going to add it to row 1. Now, technically, in order to cancel, I should have maybe put negative 2 here, but the point is that we could multiply by any row by a number and then immediately add it to another row. And so our objective is to change a matrix to what we refer to as row echelon form. Now, an echelon is kind of a stair-step pattern. And so to change this to row echelon form, what my objective is to try to get these coefficients on the left side to be ones along the diagonal and zeros underneath. I'll say that again. We want the diagonal here to be ones, and we want the bottom values to be zeros. Now, if we put it into what we refer to as reduced row echelon form, this would actually be even better. That would mean that we would also put all of the top values as zeros. But I can't just rewrite them as ones and zeros. I have to do these operations in order to make that happen. But look at the benefit of it being in row echelon form or reduced row echelon form. Since this is the x column, and this is the y column, and this is the z column, and each of these elements refer to coefficients, then this first row would say 1x plus 0y's plus 0z's is equal to that number, which would indicate that x is that number. And likewise, in the second row, that would indicate that y, with no x's and no z's, would equal this number. And in the last row, z, with no x's and no y's, would equal this number. And so our goal here is to do our best in order to move everything around, to manipulate this so that all of these coefficients become ones or zeros. Now, at first, this seems like a pretty complicated task, so I'm going to give you a pattern here in order to change each of these elements in a particular order. So the first things first, we're always going to change the first column to what we need it to be. So we're going to change the top element first to a 1. And then, anytime elements occur in two different rows, we could actually do those at the same time. So I'm going to change this value here and this value here to a 0. But then notice where I jump next. I jump into the middle. So I change this third, this fourth, and this fifth. Well, look at what that does. It changes the first column to 1, 0, 0. Now it jumps into the middle and changes this to a 1 and this to a 0. And once these are both zeros, I will then change this value into a 1. Now, if I choose to reduce it into reduced row echelon form by changing these into zeros, then the best way to do that is just to round the corner. After we've changed this to a 1, change these two to zeros, and then the last step would be change this to a 1. Now let's look at how we do this. We can only do one of these three operations. We could either interchange two rows, we can multiply a row by a number that's not 0, because if I multiply a row by a 0, just think about what that does. All it would do is change every element to 0. And that's going to prove to not be very helpful. And then this last operation is typically used in order to get zeros. It's used to cancel out a certain variable. Just like the elimination method would have canceled out variables by adding together, we're going to try to cancel out variables by also adding together. So let's look first at how we can change this 2 into a 1. Well, one thing to recognize, although there are multiple ways to do this, is that right below it there happens to be a 1. So why don't we interchange these rows so that moving this row to the top will now make this a 1, while this whole row here, the top row, will now become the second row. Now we typically write the row operation next to the row that we're trying to change, so that's why I'm just going to say let's interchange row 2 with row 1. And then in the next matrix, you rewrite it in the correct way. So all we've done is we've interchanged the second row to the first and the first row to the second, and now we realize that the top left is a 1 the way it should be. Let's look at the corresponding change in the equations. All that happened here is that I interchanged the two equations, not changing the system. Well, now I need to change 2 and -1 into a 0, and the best way to do this is to try to add opposites, just like in the elimination method. So if I wanted to cancel this 2x with the top row, then I would just say, let's multiply the top row by a -2. And once I multiply that top row by a -2, I can add it to the second equation, or the second row. So how do we write that? Well, we're changing row 2. So we want to multiply row 1 by -2 and add it to row 2. And that's why it looks like -2 R1 plus R2. Well, if you take a look at how that changes in my system of equations, we just need to do term by term. We multiply row 1 by -2, or in other words, -2, plus 2 gives me 0. So notice that when I do this, notice that when I distribute, I get -2 times 1 is -2, plus -1 gives -3. -2 times -1 is +2. Plus 1 gives me 3. -2 times -2 is +4. Plus 5 gives me +9. And so look at what this new row tells us with respect to the equation. By multiplying -2 to this equation, and then in a separate step adding it to the second equation, this is what I get. I've eliminated x, giving me a 2-variable equation. And I can see that I have a 2-variable equation because of the fact that this value is 0. Well, now we're going to do the same thing. We're going to change this bottom element into a 0. But this is kind of nice because look at how the top is already a 1. It's already the opposite. And so we should see that before we ever multiply by -2, x plus -x already cancels. So we could say to take row 3, add it to row 1, and all we're going to take is R1 plus R3. So let's do that. 1 plus -1 is 0, because x plus -x is 0x. 1 plus 2 is 3, which is why and the reason is because 1y plus 2y is 3y. Row 1 plus row 3, so -1 plus 2 gives me 1, but the reason is because -z plus 2z is 1z. And finally, -2 plus 1 gives me -1. And so what does that show as an equation? Well, it shows that because 0 is in the first spot, there is no more x. I've eliminated x, giving me only a 2-variable system at this point. Which is why, at this point, we're only going to be dealing with these two equations. We're going to completely forget about the first one for a minute, and we're going to do our best in order to get these to be a particular number. So remember that after we get 1, 0, 0 in that first column, we jump to the middle and try to get this to be a 1. Well, in order to make this into a 1, I could multiply by something that's going to make it 1. And secondly, I noticed that all 3 of these numbers are all divisible by 3. So why don't I just take row 2 and multiply by the reciprocal of -3, or multiply by -1/3. Notice what that does. Multiplying this here by -1/3, well, there is no x, so that stays 0. Negative 1/3 times negative 3 is positive 1. Negative 1/3 times 3 is negative 1. And negative 1/3 times 9 is negative 3. And look at how now I've made this middle element into a 1, which is what it needed to be. I need 1s along the diagonal. Now I'd like to get this 3 to become a 0. If I get this 3 to become a 0, that would mean that I would have to add its opposite. But look at right up above it. There's already a negative 3 right up above. And if I add these two numbers together, that won't affect this staying as a 0, because 0 plus 0 gives me 0 if I just add row 2 plus row 3. But now negative 3 plus 3 also gives me 0. And 3 plus 1 gives me 4. And 9 plus negative 1 gives me 8. And so what kind of change did that do? What that did here is just like adding the second equation in the third equation. If I want to now solve this system with only y's and z's, I can add the y's and they cancel, leaving me with 4z equals 8. Which is what we mean when we end up having two zeros here with a 4. That means that that's the coefficient of z, and if 4z equals 8, then obviously in order to solve, we just simply divide by 4, or rather multiply by 1/4. So there's no such thing as division with matrices, but what we do instead of dividing by 4 is multiplying by the reciprocal. And when we do so, notice that 1/4 of 0 is still 0, 1/4 of 0 is still 0, 1/4 of 4 gives me 1, and 1/4 of 8 gives me 2. What we have here is now row echelon form. The reason why we can actually stop solving at this point and start to find the rest of the answers is because if you look at this, sometimes referred to as triangular form, because it's 1s along the diagonals and 0s everywhere else underneath. Well, what does that show? It shows that in the second equation there is no x, and in the third equation there is no x and y. So if I start with this row echelon form and rewrite the system of equations, notice that I already know the value of z. If I plug z equals 2 into here, I could then find y. And if I plug y and z into the top equation, I can then find x. So let's go ahead and do that. All right, we can rewrite each of our corresponding systems in triangular form and recognize first that the bottom row tells me that z is equal to 2. I can now plug z equals 2 back into the z coordinate of the second equation, which would say y minus 2 equals negative 3. If I add 2, that gives me that y is negative 1. I can now plug both y equals negative 1 and z equals 2 into the top equation now, which would give me x minus 3 equals negative 2, which means if I add 3, I end up getting x equals 1. So once I used matrices to get the 1s along the diagonals and 0s underneath, I was able to just do a little substitution and find that the point of intersection is 1, negative 1, and 2. And therefore we've used matrices in order to solve this system of equations. Now this is not the only way though. I could actually continue this by turning all of these values to zeros as well. And if I do so, you're going to see why these numbers on the right would now just give me the final result. Now I already know the z value is 2. I now want to change these into zeros. So here, if I've got negative 1, in order to make it a 0, I would have to add 1. But there's already a 1 in row 3. So why don't we just go ahead and now say row 3 plus row 2, which would give me row 3 of 1 plus row 2 is negative 1. And I could also do the same thing with row 1, row 3 plus row 1. So let's see what happens there. I already have the correct form for the bottom line. And now I'm just going to add the last two rows. 0 plus 0 is 0. 1 plus 0 stays 1. Negative 1 plus 1 becomes 0. And now, most importantly for the answers, negative 3 plus 2 becomes negative 1. And if I now rewrite that equation, that means that I simply know the y value at this point because there is no x and there is no z. So the last step here is to now try to find or cancel out this term. So again, I can add row 3 plus row 1. If they weren't already opposites, then I would have to multiply by something before adding. But notice that in this case, we simply add the two together, row 3 plus row 1, and notice I'm going to be left with 1 plus 0, which is 1, 1 plus 0, which is another 1, negative 1 plus 1, which makes this 0, and finally negative 2 plus 2, which makes this 0. Now we're not quite done because notice that 1 and 1 indicate that those are the coefficients of x and y. My last goal here is to turn 1 into 0 in order to cancel out these y's. So what do? I simply multiply 1 in the second row by a negative, so that when I add them together, that will now be 0. So we say negative 2 plus row 1, or negative row 2 plus row 1. So we change the sign of row 2, one term at a time, and then we add it to row 1. So we can already see the bottom two rows stay the same. Negative 0 is 0, plus 1 gives me 1. Negative 1 plus 1 gives me 0. As it should, because that's why we chose that row operation in the first place. Negative row 2, so negative 0 plus 0 makes this 0. And lastly, negative row 2 times negative 1, right? I'm sorry, negative row 2 plus row 1 means multiply negative 1 times a negative to get 1, add to 0, and I finally get 1. Well, look at what this top equation looks like now. It means 1x plus no y's plus no z's equals 1. Look at the benefit of converting into reduced row echelon form by making the main diagonal 1s, but everything else into 0s. It's because it tells me automatically what the values of x, y, and z are in this final column. So if you didn't choose to stop with row echelon form and you decided to change each of the top values to 0s as well, you would end up getting your final answer as that last column.